All right, we're ready for the sixth lesson of the unit, and I believe the final lesson for the unit here. Remember, our essential question is how do the properties of subatomic particles determine the different chemical properties displayed by atoms of each element? So I'm going to keep the same sub-question from yesterday. How do scientists use knowledge about electrons and energy to predict the behavior of elements? Uh, because I think electron configurations are really a next step in that. Uh, and when it comes to electron configurations, and even yesterday with quantum numbers, I probably should have said this. For the first half of this lesson, and maybe even throughout this lesson and half of the practice problems, you're going to really probably struggle to understand it. I'm going to have a lot of people who are frustrated with it. So I'm asking you guys to bear with me on that. I know it's frustrating. I know this is different. But if you give it some time, I've taught this semester after semester here now, you start to see the light bulbs going on. And then within a couple of days of practice, I think most of the students are going to be looking back wondering, oh, how did we not really get this? And it happens that way every time. It's really hard to get until you kind of have a complete picture of it, and then it starts to make sense. So we'll jump in here then. Electron configurations are the ways in which electrons are arranged around the nucleus of an atom in the ground state. So there are some rules for filling orbitals, and I just want to rehash some vocabulary. Remember that, so when we're talking about electron configurations, there's going to be a configuration for each electron, but the configuration for the last electron kind of tells us about all the different electrons in the atom. And orbitals are regions of space that an electron can be in. So rule number one is the off-bow principle. It says that electrons enter the lowest energy sublevel first. Not necessarily the lowest energy level. We're going to see some sublevels kind of switch around, but the point here is that electrons will go to the lowest energy sublevel first. Orbitals within a sublevel are equal in energy, and so that leads us to the off-bow diagram, which we have here. This is actually an ordering from lowest to highest energy. So think about it, the axis, the vertical axis here is energy. The 1s sublevel is the lowest, then the 2s, then the 2p, etc. And then if you look on the same sublevel, like all the p's, the 2p's have the same amount of energy. And then 3s and 3p and 4s. We'll notice that the 4s sublevel is actually before the 3d sublevel. That's what I was talking about when I said that it's not necessarily the energy level. Sometimes a fourth energy sublevel, like the s sublevel, will have a lower energy than the 3d sublevel. That is because of the space in which the electrons are traveling. The spherical shape of the s sublevel gives it a lower energy than either the figure 8 shape of the p sublevel or the cloverleaf shape of the d sublevel. And so that's why here that even though the electrons are further away, because they're moving in a spherical shape, 4s is at a lower energy level than 3d. The second rule is the Pauli exclusion principle. It says that no two electrons can have the same 4 quantum numbers. Two electrons in the same orbital have to have opposite spins. So you see on the left here, that's the correct way to show two electrons on the same orbital. And then with both arrows pointing in the direction, that is not allowed. That is incorrect to the right. And the third and final rule here is Hund's rule, which says when filling orbitals of equal energy, one electron must occupy each orbital within a sublevel before pairing begins. So single electrons must have parallel spins. And you see here 3 different pictures. The left and the middle are incorrect. I'm just going to focus on the right. If you have 3 electrons, one should be in each of the 3 sublevels available. They'll all spin the same direction. We just always call that spin up first, and then we fill in the down spinning electrons. There's this diagonal rule here, which I don't love, but the way that it works is you can draw a diagonal line through going from the top right to the left. And if you go by row, I'll show this in class, but you would have the 1s2, and then you would have the 2s2 before you get to 2p6, 3s2, and you keep drawing those lines diagonally, and it tells you the order. The way that I like to learn the order of the sublevels is by looking at the periodic table right here. And you read the periodic table just like a book. You start at the top row and you read left to right. You're in the first row, so that's the 1s2 because there's hydrogen and helium in the 1s2 sublevel. So we have 1s, then there's nothing else in the first row, so we have to go down to the 2s sublevel, and then we read across, we go over to the 2p sublevel, and then we're out of the second row, so we go to the third row. I'm over where the element sodium is. There's the 3s sublevel. I have to keep going across to the 3p sublevel. Now I'm at argon. I jump down to the fourth row of the periodic table where element K, potassium, is. That's the 4s sublevel. It's not till we get to the D sublevel that we have to do some trickery on the periodic table. Even though we're in the fourth row, because the 4s sublevel fills in before the 3D sublevel, the D sublevel is a row lower on the periodic table than it should be. So even though we're in the fourth row, we subtract 1 to make this the 3D sublevel. And if you count across the D sublevel, there are 10 electrons in the D sublevel. After that, we move to the 4p sublevel from gallium to krypton. Then we go to the next row, 5s, 4d, we always subtract 1 from the D sublevel, 5p from indium to xenon, and then we go to the sixth row with cesium and barium as 6s. Then we have a little bit of a trick here. If you look at the atomic number, barium is 56, and we're told that we actually have to go down to the bottom of the table for elements 57 through 70. The reason the F sublevel is drawn down below is if you inserted that up into the body of the main periodic table, the periodic table would become very, very wide, and it wouldn't really make sense. It wouldn't fit on a single page, I should say. It would make a lot of sense to put it there. So we just put that little blank space there, and then we see the lanthanoids there, which are the 4F sublevel. We actually subtract 2 rows from the F sublevel. So instead of being 6F, it's the 4F sublevel. The reason is because the same thing for the D sublevel, the F sublevel has an even more complex shape. And so those electrons, even though they're closer to the nucleus, they don't fill in until much later in the process than the rest of the fourth energy level. Then we go back to the 5D sublevel from 71 to 80, and then the 6p sublevel, and so on. On the periodic table, we stop then at 7p with element 118. We don't know of any elements beyond that to get into the 8th row, but element 119 would theoretically start the 8th row. It would be a long time before we introduced a G sublevel. It would take a while to get there because the F sublevel, didn't fill in until the 4th row, so we would end up having a 5G sublevel, but it would be after the 8S sublevel anyway. So I'm going to go back then to what we were just talking about, and I want to make an analogy here. I tend to think about students filling onto a bus. And typically, when students get in the bus, at least back when I was a student, students like to sit in the back of the bus as far from the bus driver as they could. So I almost think of the distance from the bus driver as the energy level, and students would get onto the lowest energy level, the furthest away from the bus driver and closest to the back of the bus. And then the seats on each level, they're equal with each other. So probably what would happen is one person would sit to the left, the next person would sit to the right, and then they'd start kind of partnering up in the back of the bus as we kind of start to fill up the back of the bus, and then students move up to the next row and the next row and the next row. The reason I like this analogy is, are there any seats on the bus that you might skip over even though they're technically a lower energy level? I hope you're thinking about the wheel seat in the bus. A lot of times students didn't like sitting with that wheel seat, so they might skip over it, and it might not fill in till later. And that's exactly what happens with the D and the F sublevels. So hopefully that analogy helps you a little bit. Now we need to get some practice doing a few things. We're going to write electron configurations. We'll start out with an orbital notation, then we'll do the full configuration, and then we will do a noble gas configuration. And I'm also going to ask a couple other questions as we go through these. But the first element here is carbon. So when I talk about an orbital notation, I'm talking about drawing out these platforms. So the 1s orbital notation, we have to look at the periodic table and count up. Carbon should have a total of 6 electrons. The first 2 will always be in the 1s sublevel, the next 2 in the 2s sublevel, and then after that, there's only 2 left, so we fill in the 2p orbitals, spin up and spin up, and so this is our orbital notation for carbon. Now, once you have the picture drawn, it's really easy to do the configurations. It's a little harder to do them from scratch, but it's certainly possible. It's just 1s2, 2s2, and this should say 2p2 here. I'm not sure why I have a 1 there. It should be 1s2, 2s2, 2p2 as the full configuration. Now, the noble gas configuration looks at the periodic table. So generally what you'll do is you'll go from carbon over to the nearest noble gas, and then you'll move up a row. And we're going to write that noble gas, which is helium, in brackets. This allows us to shorten the full configuration, and this should say 2s2, 2p2 as well. So it's helium, 2s2, 2p2. The orbital notation is correct. You just need to tweak the full configuration and the noble gas configuration. Now, with this particular problem, it didn't save us much time writing helium instead of the full configuration, but that will save us some time later. So we'll try calcium. And I really encourage you to try this problem on your own and then check the answer. So maybe pause the video, get the orbital notation, the full configuration, and the noble gas configuration, and then check your answer. If you're checking back now for the answer, here's my orbital notation for calcium. We have the 1s is filled, the 2s is filled, the 2p is filled, the 3s is filled, the 3p is filled, and then there are 2 electrons in the 4s. If I glance back at my periodic table, this will just take a second. You should be able to check your answer with this because calcium is in the 4th energy level, or the 4th row of the periodic table. Calcium is in the 4th row. It's in the S sublevel, and it's the 2nd element in there. So it should end its configuration with 4s2. And just to remind everyone with the carbon example, that one should have ended in 2p2 because it's the 2nd row, it's in the p sublevel, and it's the 2nd element in the 2p sublevel. So that one was 2p2. Calcium here ends in 4s2. Now, we have to write out the configuration for all of that, and you can do this just looking at the periodic table, or you can look at the picture that you have. Sorry about all of that. So the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. On the test, you will have to be able to do this from just looking at the periodic table, kind of reading it like a textbook, going across the row and then down to the next until you get to the element you're looking for. Now here, the shorthand configuration really saves us a lot because everything up to 3p6 gets lumped in with argon's configuration, and so then we finish with just the 4s2. And my last example is zirconium here. Remember, please try to do this problem on your own and then check it. And if you're checking back in, here is the answer. Zirconium has all of these sublevels filled up here up until the 4D sublevel, where there are only 2 electrons in the 4D sublevel. The configuration then is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d2. And then if we simplify this, everything up to 4p6 is covered by krypton in brackets, so 5s2, 4d2. The reason that we work on these shorthand configurations is because typically we're most interested in the electrons that are furthest from the nucleus, that are in the outermost energy level. And so generally when we cut it off at the noble gases, that's going to give us the most information, or the important information is still all visible. We'll get into that really in the next unit. For now, I want to answer just a couple more questions about zirconium. A couple questions you might see on the test might be something like, what is the final term for the differentiating electron? Remember, the differentiating electron is the last electron. It's the electron that makes this element different from the one before it and the one to come after it. So 4d2 is the term for the last or differentiating electron. So you could get a question like that. You also could get a question that says, what is the highest occupied energy level? In this case, that's the 5th energy level. The differentiating electron is in the 4th energy level, true, but the highest occupied energy level is the 5th energy level. The last question you can get is referring to the number of unpaired electrons. So the question might be, how many unpaired electrons does zirconium have? And the answer to that would be 2 as well, or 2 in this case, because if you look at the 4D sublevel, all the other electrons are paired up, which means there's one spinning up and one spinning down. But in the 4D sublevel, both of those electrons are unpaired. Unpaired electrons they're important because they shed some light onto properties like magnetism and the color given off by different elements, and we will study that a little more as well as the year progresses. So all of those kinds of questions are actually fairly important. As I said, the differentiating electron determines how elements behave, kind of similarly and differently from their neighbors. The number of electrons on the outermost energy level oftentimes tells us about bonding, or the highest occupied energy level. And then we said that the magnetism and color can be determined from thinking about the pairing of electrons. So let's see here. I can also ask you how many electrons there are per energy level. So I just took that configuration over to this page. The electrons per energy level, well, the first energy level has just the S2 sublevel, so that's 2. The second energy level has the S2 and the P6, so that is 8. The third energy level has 2, 6, and don't forget the 3D10, that's 18. And the fourth energy level has 2 on the S, 6 for P, but only 2 for the D sublevel, so that is 10, and then the fifth energy level has 2. The dot diagrams, we haven't gotten into this yet, but we will be in the coming units, so it's a good practice. In this case, we're going to take the number of electrons on the very outermost energy level, and we're going to put them in dots around the symbol. So we'll have the ZR symbol. We'll put a dot on top and a dot to the side. You would put one dot on each side, and then you would start pairing them up. This goes with the octet rule that we'll learn about in the next unit, saying that elements bond so that they can have 8 electrons in the outermost energy level, and the dot diagram is a very quick way to show how many electrons the element has in the outermost level. In this case, there are only 2, and that's going to tell us a lot about how atoms are going to bond with other atoms. Finally, the differentiating electron, we want to know the quantum numbers for the last sublevel, or the last electron. So if I look at that last electron, it's on the 4th energy level, actually, It's in the D sublevel, so S would be 0, P would be 1, D is 2. I'd have to write out in the D sublevel 5 platforms, which I would label -2, -1, 0, 1, and 2. And then because this is the second electron in there, that would be a -1, and it's going to be an up arrow, so it's +1/2 for the differentiating electron. There are some exceptions that occur as well in the D block, and we're going to look at 2 examples like that. Elements in group 6, like chromium. Chromium, if you do this problem on your own, you should get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. That's what the configuration would be, and I always like to write that out first, and then I kind of make the adjustment. Some of you guys will get really good at this and you won't have to do that, but if this is confusing, write out what it should be, and then we're going to make this little change. Chromium is going to move one of its electrons from the 4s2 sublevel into the 3d sublevel. The reason for this, the theory is that there's an energy benefit to having a half-filled sublevel, and so the element benefits from having the D sublevel half-filled at 5, and all it has to do is move one electron over, and so it would prefer to have a half-filled S sublevel and a half-filled D sublevel than to have the 4s2 3d4 configuration. And when I say it would prefer to, what I really mean is that the atom decreases in its amount of energy. That's what governs the way atoms behave, is they are trying to get the lowest amount of energy possible. That's why electrons prefer to be in the ground state, and the ground state for chromium is going to be 4s1 3d5 because of this exception. We also see this in group 11. Copper should have a configuration ending in 4s2 3d9. If you guys would please make the change and then check your answer. And if you're checking back, the answer should be that it ends in 4s1 3d10. There's also an advantage to having a full D sublevel, and the half S level. So that is why this column ends in 4s1 3d10 as opposed to 4s2 3d9. Might not be a bad idea on your periodic table to kind of highlight columns or group 6 and group 11. So that's chromium down and copper and down, because you could be asked about those exceptions on the test. And I do have a challenge problem here. Let's see. We want to answer the following for gold. So I will let you guys answer this on your own, and then we can check back with the answers. The full configuration for gold is this. It ends in 4f14 5d9. Actually, I should have included the 6s2 4f14 5d9. That's the last row there. The noble gas configuration. And gold actually is in that column that is going to be an exception. I should have noted that, group 11. So this is actually very important to kind of take a look at. The F sublevel won't be where we move the electrons from. Once those electrons fill in, they're all the way down on the 4th energy level. So gold is going to move an electron from 6s2 over to make that 5d10. So the red is the correct answer for that. The noble gas configuration. Now we're just going to chop everything off 5p6 and below, and we're going to call that xenon. Makes this much easier. Let's see. I think that 6 that's in there it should say xenon 6s1 4f14 5d10. There's a superscript 6 that got left in there that should have been cut off. What are the 4 quantum numbers for the differentiating electron? Well, that's the 5d10 electron, so n equals 5, L equals 2. The spin quantum number, we'd have to set out the 5 platforms here, and since they're full, this is going to be the last platform, the +2, and the spin is -1/2, it's spinning down. How many unpaired electrons does gold have? It is going to have 1 unpaired electron in the S sublevel, and the highest occupied level for gold is the 6th. So that is the end of this unit. So we'll have a little bit of review, but make sure that you're aware of the date of the test, and good luck.